Yes, all good. Okay, let's start. So today we'll have a presentation by Kenric, who is working at Fortrek and recently joined us in our DCM meeting, and is going to be talking about some measure of statistical nonlinear coupling, which is a very promising use for estimations of various type of model. So Kenric, over to you.
Yeah, well, thanks for asking me to talk a little more about the coupled free energy and how it can be used to learn extreme models. My co-authors in this work are Igor Oliveira, who's joined, and also Amina Al-Najafi, who's joined. So I'll go through an introduction and I'll frame it a little bit in terms of some of the things that you all might be interested in. And then I'll dive into modeling complex systems. And the model we're using is what I refer to as a coupled exponential family. And then that motivates a generalization of entropy. So I'll review some prior entropy functions and then make the case that I've completed a proof of why the coupled entropy is unique. And then it has unique properties that I think are going to be very promising for use in both variational and active inference, which would be your interest for this group. And I'll show a few results with a coupled variational autoencoder. Just some background about myself. So I launched Fortrek about 5 years ago. We're focused on building a risk governance platform, and we draw from skills both in this analytical machine learning that I'm going to show you today, and then also in developing protocols for DAO community governance. And both of those together, we think, can have an impact on modeling and mitigating catastrophic risks like global warming. We are a broad global team. I work out of the Boston area, just outside of Cambridge, Massachusetts. But everyone else is in the team. So Igor, for instance, is in Brazil. Amina is in Iraq and is currently applying for a role in Portugal. So you're going to hear on that soon. I'm formerly a research professor at Boston University, where I was collaborating with Mark Kahn and Eugene Stanley. And then a lot of the early work in these techniques was in a collaboration with Sabir Umarov, and before that, Konstantino Salas. And currently, Ugur Turkneli at the Izmir Economics University in Turkey is a strong collaborator. In fact, I was living in Turkey for 2 months, working with him this past year. So let me kind of frame the challenge. While artificial intelligence has really exploded in capabilities around deep learning, most of the infrastructure of AI and machine learning is centered around the properties of the exponential family, and from that, the properties of the Shannon entropy function. Now, you can do quite a lot, obviously. These tools are quite sophisticated in the way they can be used to build big, complex systems. But it is hard to incorporate into that the nonlinear, non-equilibrium dynamics that produce heavy-tailed distributions. So when it comes to modeling extreme weather or financial crashes or other places where nonlinear dynamics are quite important, and ultimately you have divergent means and covariances, then the traditional models break down. So as one example of that, in emerging markets, there's a lot of fluctuations in the prices or the return on an asset. And an example of that is the Bitcoin returns over the last, this chart is from 2010 to 2018. And all of these, the central part of that is like a Gaussian kind of distribution, but all these spikes throughout it are fluctuations in the variance. that create a heavy tail distribution. Um, and this can be modeled with agent-based modeling that Andre Villela's team does and we collaborate with, which is the plot in the middle. And we see here very precisely what we refer to as coupled Gaussians as a really good fit for this dynamics. Or it's traditionally called the student T distribution. They're exactly the same. The degree of freedom, if you invert it, turns out to be equal to the nonlinearity. And we're going to dive into that a little bit more. But before I do, I want to set the context for what I think might be of high interest to your group. In the free energy principles, an important concept is the Markov blanket, where you define a independent system to have a Markov blanket in which its properties, its internal properties are independent of the properties outside in the environment. And the definition of that Markov blanket is an important part of the free energy principle. Inside the system, you can have correlations, and that in the upper right hand side here, I have a Markov field with pairwise correlations using an exponential function. And these pairwise correlations are essentially what you learn in your machine learning techniques. But you're expected at the boundary to just, for all of those to be zero, and anything that's between the internal and external would just have the marginal weights here. Well, it turns out with this coupled algebra, one of the things you can do is you can have the matrix be just the independent marginals here. However, you build a long-range correlation by not using the exponential function, but a generalization of that exponential function, the coupled exponential. And I'm going to go into that in more depth in a moment. But the key thing here is that it is a way of modeling a nonlinear dependence between the elements of the system, including potentially across the Markov blanket. And what way that happens, or part of how that happens, is you get a generalization of Bayes' rule. So traditionally, when you model a dependence between, that A is dependent on B, and then you have Bayes' rule where you have the likelihood function. Traditionally, that would be multiplied by an independent prior on A. But here we can modify this so that it's not independent, but rather has a nonlinear dependence. And this nonlinear product function has a function where you raise both probabilities to a power. There's a -1 term here that we'll explain in a moment. And then the whole thing gets inverted by 1 over this coupling term. So I'm going to go into this more. So in a moment, I'll sort of pause and we can take questions on this. But let me press forward for a moment here. So the way the starting point of this generalization is a generalization of the family of probabilities. The exponential family is the one that's used the most. And the way the exponential family is defined is you have an exponential function, and then inside that exponential function are the parameters of the distribution multiplied by a dot product with the statistics, like x or x squared. And then outside of this, traditionally, you have an h of x, which for this discussion, I'll just set to 1, but it can be more general than that, divided by a normalization, often referred to as the partition function. So we're going to generalize this now. Instead of an exponential function, we're going to use a coupled exponential function. And it's going to be defined by 2 parameters, alpha and coupling, and it's actually going to be raised to an additional power that becomes important. But the beauty of this is I preserve this structure of still having parameters with a dot product and a statistic. And this normalization is still on the outside, but it can be brought in with something called the coupled sum product function. I won't go into that as much depth today, but the key thing here is that what the coupled exponential function does is it gives you a family of power law functions. And then this coupling term, when it converges to 0, this is the function that converges to the exponential. So you can think of, so 0, this would be infinite. So the exponential, remember, is the fastest function that goes to infinity. And now we can modify that and have all the powers that go to infinity, but at slower rates. And then we can also invert this, and then you see the nonlinearity even clearer. So x to the coupling, this coupling defines the nonlinearity. And again, you need this -1 term so that it'll converge to the logarithm. And again, when you zero, you can think of this as the slowest, for the logarithm, it's the slowest rising function that goes to infinity. And it turns out that the dimensions of the distribution and this alpha parameter that is a location parameter or a shape parameter near the location are critical to getting the definitions correct. And the two functions that we're going to be primarily interested in are the generalized Pareto distribution, which will have alpha equal to 1, and I refer to as a coupled exponential, and the student t distribution, which is alpha equal to 2, and the coupled Gaussian. That's the one that will be used in machine learning quite a lot. And the key thing here is that the moments can diverge. When the coupling is above 1/m, that moment diverges. And so in particular, when the coupling is greater than 1, all of the moments diverge. And we're going to look at those extreme cases and show that there are still ways to learn those distributions in a machine learning algorithm. So the coupled Gaussian is the place to start. The black curve here is the traditional bell curve Gaussian that we're all quite familiar with. And then the blue curve is actually a compact support distribution that decays faster and then has it truncates with a range of where the probabilities are all 0. For this talk, I'll mostly concentrate on the heavy tail distributions. The Cauchy is shown here in red, where you get like a sharper peak near the location, and then you get these long tail decays. And the way this is structured, so again, if you're familiar with the student t distribution, 1 over the coupling is the degree of freedom parameter. This 1 here is the dimension, so this will generalize to d for multiple dimensions. And then the crucial thing is this I've proven recently is the only way to define the scale of these distributions such that that scale is independent of the coupling parameter. There's been some other attempts to define these distributions in other ways, but if you don't do it this way, the mathematics is not going to work out correctly. And one of the earliest things I showed is that this is now precisely the shape parameter of the distribution or the tail decay, and that is precisely equal to a source of nonlinearity in a system. So I refer to this as the nonlinear statistical coupling, or more recently we've been calling it the nonlinear shape. And I've also shown recently that that's proportional to a measure of complexity. Before I go further, this is a good place to pause. Are there any questions about this just foundation of the coupled exponential family? Anyone got some insights or questions about how the coupled exponential family is defined?
Maybe I could ask for clarification.
Sure.
So you said that when kappa equals 0, it converges to the normal exponential, but I don't see why this would be the case.
Yeah. Sure, that's a great question. So if we look at this function here, this is going to go to infinity. The exponent's going to go to infinity, and this is going to go to 0. Now, I'm not really showing exactly why, but in the limit, this actually is the definition of a exponential function. In the limit, as this goes to 0, you get the exponential function. It's maybe, and likewise with the log. Now, I'm trying to think if there's some way I can provide some intuition. Well, maybe I'll tell you, I'll show you actually, maybe let me skip a slide and go right to this. And with that question in mind, I'll introduce this slide where you see the family. And maybe that gives you a little bit more clarity as to why it converges to the exponential family.
Yes, thank you.
Yeah. So this now is the coupled exponential distribution, which is a one-sided distribution. And this first curve is one of these, has a coupling of minus 0.33 and has this truncation. It's a little off screen, but with the scale equal to 0.5, you can see the truncation is around 1.5, and then everything else is 0. And then when you go to 0, which is the next curve here, this is the exponential distribution here. And you see that it still has a very fast decay, right? And that will go all the way out to infinity and still not be 0. But it converges to 0 in the asymptote. These other curves also do eventually go to 0, but they go to 0 at a much slower rate, and they're referred to as heavy-tailed distributions or fat-tailed distributions. And the interesting points here, so with the coupling equal to 0.5, at that point, the variance is no longer finite. So the fluctuations are quite extreme in this kind of a distribution. And then when you get to a coupling of 1, you're no longer able to define a mean. And when you take samples from that kind of distribution, what happens is you can always measure a mean, but the next sample can make it go from literally from 0 to infinity. So there's no way, it won't converge to the mean from sampling. Now, this plot is a little bit complicated, and I'm showing this before I discuss any of the functions about entropy, but I do this for a point here. There's often not good intuition about what entropy is measuring. People are very clear about what a mean is. They're very clear about a standard deviation and a variance. You should think of those are measures along the random variable, along the x-axis. You should think of entropy as being a measure along the y-axis or along the probability or density domain. The reason the intuition is not there is because in addition to taking an average along the y-axis, you also take the logarithm. And in taking the logarithm, you're moving to a different space that's not really represented in this graph of the probability distributions. Now, what I've done here is I've taken the entropy measure of each of these distributions and I've mapped it back to the density space by taking the coupled exponential function. And that maps it back. And thereby the average over the distribution in the same way that when I take the mean, right, that's a mean across the whole distribution, and it represents a single point that's a central tendency. And likewise, this scale for the exponential family is the standard deviation along the x-axis here. Now, the key thing is that for the exponential family, when you measure the Boltzmann-Gibbs-Shannon entropy, you get this point right here on the scale. And then if the coupling is, plus the coupling adds a linear term to this. So these blue ones quickly move away from that scale because of the dependence on the coupling. And this is essentially what motivates the desire for a generalization, because Once you go into this heavy tail domain, the entropy function is going to be dominated by that, and you kind of lose sight of the uncertainty due to this scale parameter. And importantly here, another thing I've shown recently is that the scale across all this whole family represents the source of information from a linear source, whereas the coupling is representing a source of information from a nonlinear source. Now, starting in the late 50s, soon after Shannon did his work, Alfred René proposed a generalization of the entropy that's known as the René entropy. And at the heart of what he did, so the Shannon entropy is really taking the geometric mean of this density or probabilities. The René entropy instead takes a generalized mean, and there's a kind of one-to-one mapping between the generalized mean that you use and the tail decay. And the René entropy does do something useful here. It pulls it back in so the metric is closer to this scale. More recently, there was work by Salas, and I've collaborated and sponsored his work, and there were important innovations that came out of that work, but I have recently shown that it is not actually a metric. I'll show it in the next chart a little bit more. And finally, basically what I'd say is there is a requirement for a generalized entropy that has not to date been documented, but I'm now saying is a strict requirement, is that your measure has, that number one, you have to use this parameterization of the generalized, of the heavy tail distributions in order to get the right scale. And then your entropy measure has to be a measure of the uncertainty at that scale. And I show that that's only satisfied by this coupled entropy. And, you know, this was kind of the, I actually defined this about 10 years ago, and I asked people working in generalized entropies to study the properties, but I never got anyone to take it up because there were so many proposals. And this past year, I was going back through those notes based on some breakthroughs in our machine learning. And I realized that the solution for the coupled exponential could be encapsulated in this equation here, where it's 1 plus this particular generalized logarithm of the scale. And I understood at this moment that there was something perfect about this solution that I needed to understand. And that's when I dug into this and developed the proofs around it. And just to put this in context a little bit more, this slide is a little bit busy, but if we look at these entropy functions as you increase the coupling, so again, this is still the coupled exponential distributions, you can see how the Shannon entropy goes to infinity very quickly, and that the René entropy basically takes the log of this. And it's going, the Shannon entropy is going to infinity because of this linear dependence on the coupling. The René entropy changes that into a log of the coupling, which is definitely a useful thing. The Salas entropy approximates what you want, but in the end, it converges to a constant. So as you get more complex systems, it no longer is a metric. And there were proposals early on to normalize it in a particular way, but that normalization ends up blowing it up, was shown quickly to be unstable. And basically what I've shown is that there's an additional normalization that was missing from this structure that now forms the coupled entropy. And so you get this beautiful metric where regardless of what the coupling is, you're pretty much measuring the same thing. And so there is this generalized logarithm, but that's kind of soft in terms of what its effect on this metric is. It's dominated by the scale, and that's what I'm saying is exactly what's needed. And so now the way I think about the coupled entropy is that it's a way of separating the metric between the nonlinear source of information and the linear source of information, where the scale is what's creating a linear uncertainty, and the coupling I want to separate out as the nonlinear source of information. And so it's still, and the other thing too is it's not, I don't see it so much as replacing the Shannon entropy as complementing it and giving you an additional metric that gives you more fine detail about the properties of systems. Okay, so now diving into the mathematics a little bit more. The coupled entropy now has two components to it. It has this generalized logarithm. That's sort of the key innovation. And this part of it is similar to what Renee and Solis were doing. And it is specifically this function where you take each probability, you raise it to a power, subtract one, and then normalize that. One of the key innovations in this is this recognition that it is not just the coupled logarithm that you need, because the weights here on the exponent and the normalization have to be different. And they're different basically because of the dimensions of the system. 0 would be the cumulative distribution. So the cumulative distribution is where these two things equal each other. And then every time you take a derivative for each dimension, this exponent changes. But the real innovation and why it's going to be significant in machine learning comes from what's called the independent equals probability. In the Solis literature, this was referred to as the escort distribution. And this exponent here, 1 plus alpha kappa divided by 1 plus d kappa, that is precisely the Q parameter, and also the Renee alpha parameter. So that's where this is what connects the coupled entropy work to Solis and Renee. But another key thing here is that Q parameter is not fundamental to complex systems and is part of why the mathematics of that approach didn't really work out. You have to there's actually three things that matter here. The nonlinear shape is the thing that matters for complex systems, but you have to separate out the shape that's due to alpha near the location and also the dimensions. So when we do this, when we take a probability distribution, particularly from this coupled exponential family, and we renormalize it, we rescale the covariance, I should call them correlation matrix, by this 1 plus alpha kappa. And then also it rescales the coupling. And in particular, this rescaling of the coupling is going to ensure that all the moments converge. That's the key thing. You're going to make sure that the moments converge. All right, so now, and again, actually, this is maybe another good place to pause. I've gone through kind of the heavy part of the mathematics now. Is there any clarification of that before I press forward with the applications?
Yes, I would have a question. In terms of like the coupling, what are you what is exactly the coupling coming from, and how to understand it in the case of complex systems? Like, is that
Right.
Analogous to, like, for instance, like the relationships, like the degree of dependency of one like differential equation onto another like one state variable, or is that unrelated to that?
Yeah, excellent question. In fact, I think might be a good thing to add to the presentation here. So if I flip back just a little bit, just as the exponential function is the solution to linear differential equations, this coupled exponential function is the solution to nonlinear differential equations. So that is precisely it. It's moving to nonlinear differential equations that you get this equation. I would be a good thing to add right here. But there's another thing too that originally why I used this phrase. I was trying to understand what this independent equals distribution is. And one way you can picture it is that it's a coupling between all the states of the distribution. So if this if the original probability is giving you the probability of each state and you treat each of those states as being independent of each other, you can think of this independent equals distribution as looking at one state, but then multiplying it by all the other states raised to a power. And so you're kind of looking at one model of this one of the important models here is what's called incomplete statistics. If somehow you have a distribution, you have a set of states, but somehow the definition of what the probabilities of those states isn't very clear. So that's two cases, but also just generally, it is, I would argue at this point, given how many times I've been successful in showing this, that if you have a heavy-tailed distribution in a system, if you measure that in your data, then you can always tie the tail shape back to a source of nonlinearity, and they will be equal to each other. There is some nonlinear source of that tail decay.
I think Anthony has a question.
Yeah, go ahead, John.
Sorry, so I'm a total non-mathematician, but what I'm picking up is there's both linear and non-linear components to what happens in complex systems. The classic one being climate change.
Yeah.
And when people project into the future, it seems that most of the models assume only linear kind of things that are going on over the next. I mean, I'm sure there are some that don't, but this strikes me as something that will be very useful for us when we start looking at the impacts on climate, for example, on nutrition, very complex relationships.
Right.
Am I right in assuming that this is a mathematical way of coming up with different models with different components with more nonlinearity or less nonlinearity?
Yes.
Is that exactly what this is about?
And the other, when we get into risk modeling too, there's actually another dimension too. So if you recall the history of the development of the student T distribution, it was invented by Gossett, who was an employee of Guinness Brewing Company. And the problem he was trying to solve is in their processes, he understood that the process was Gaussian, but he only had a limited amount of data in order to measure the variance. And so he figured out that with a limited, that he could tie the amount of data points that he had to a degree of freedom. And that degree of freedom would define the student T distribution. Well, you can generalize that more in any kind of training of an AI system. There are going to be differences between the training set and how you actually use it out in the field. And that creates risk because there's some additional uncertainty that's not captured by the training set. So the very first paper we did on the coupled variational autoencoder was focused on making the training process more robust against distortions that weren't in the training set. And we were able to show that. And we think is a significant use case for these techniques. Great, those are really helpful questions. So now let's dig into the applications. I see I'm going a little bit long, but nevertheless, I think you'll find this interesting. So the two applications that are high interest with this group are the variational inference and the active inference. I'm going to mostly talk today on variational inference, but I think once I'm done, we can maybe open up the discussion to how it would apply to active inference. And of course, the point here is that oftentimes the distributions you're trying to learn are quite complex, and you can change that into an optimization problem in which you're trying to learn a approximation to it by modifying the parameters. And the way you do that is that you minimize a negative free energy, or excuse me, you minimize a negative evidence lower bound or the free energy. And then likewise, active inference is, of course, it has broad applications, but one of the things that was impactful to me in learning about these techniques is that now you can also roll into it not just inference, but also all the planning and the decision making that goes into robotic control of processes. And that's done through measurements of the expected observations. All right, so I'm going to show our work has focused on the variational autoencoder as a kind of demonstration of this. But again, we're generalizing the free energy function. So anywhere that function is used, these techniques would be relevant. And just as a recollection here, the variational autoencoder takes a complex data set, like a group of images, encodes them with a neural network into a latent space that is learning some distribution. Typically, that is a multivariate Gaussian. And it still can be complex because it's not one multivariate Gaussian, it's a whole mixture model of multivariate Gaussians. But the key here is that the tail decay of that model is exponential. And then you can sample from that latent space, decode it, and get an output. And in your training process, what you're doing is you're doing this repeatedly, and you're seeking to minimize this negative elbow or free energy function that has two components to it. It has a measurement of the quality of the reconstruction, and then it has a measure of the complexity of the model, which is a divergence between a prior and the posterior. So when we go to generalize this, I'm going to focus today on an approach where we generalize everything throughout the whole model to have a matching value of the coupling. You don't have to do it that way, but the mathematics does simplify quite a bit when you do that. So we're going to have a coupled Gaussian as the latent distribution. We're also going to have a coupled Gaussian as the model of the noise in the pixels of the image. And then that's going to generalize, our metrics are going to generalize the divergence and likelihood metrics. And the key innovation here is that when we do the training, we're not going to sample from the latent distribution. We're going to sample from its modified independent equals equivalent, where you raise the probability to a power and renormalize. And now alpha is equal to 2 since we're using the Gaussian. And that creates this situation where the coupling now can go from 0 to infinity, but my training samples will have a coupling value in the limit of 1/2. 1/2 is the boundary that guarantees that it has a finite variance. So however complex my model is, my training samples are guaranteed to be well behaved. Now, I'm not showing the derivations here, but one of the things that's really nice about this is when all of the coupling match, you get a significant simplification. So there are some additional constants here, but the metrics themselves are pretty much the same. You're measuring essentially the melanomus distance between the prior and the posterior, just as you would with a standard VAE. And then, so that's your complexity measurement. And then with the accuracy measurement, you're still measuring the mean square average of your results, but now you're doing the expectation over this sampling, not from the latent distribution, but from this modified independent equals distribution. And, essentially there's no, we can show that you can go near to infinity essentially with your coupling value now with your model and still have the training process converge. And this is new. the we have a paper that's titled Coupled Variational Autoencoder that was published around 2020. But there we were sampling from the latent distribution, and it didn't converge. Between like about 1/2 to 1, you would start to see numerical problems in the calculations. And that wasn't unexpected because we knew the variance was going to infinity. But now the way this works, I'll just kind of show this both this is a log linear plot on the left and then a log plot on the right. So if we start with this light blue curve here, this has a coupling of 10 to the minus 5, which is just essentially 0. So this is your Gaussian. And there's no change with the independent equals one. It's approximately the same. And then you can see here how it drops off very fast. That's that very fast exponential decay. And then we can go to the Cauchy distribution where the coupling is equal to 1, and we get this very flat curve, and you can see how you get this slower decay here. But when we take the independent equals, now the coupling is 1/3. And so you can see that it has a faster decay here. It's not exponential, it's still heavy-tailed, but it's faster. The other, just to note here too, one of the ways the scale is defined is the scale is the knee here. And it's exactly the point where this log plot is -1. And that's true for the whole family of the coupled exponentials. So that's what defines the proper scale. But finally, the interesting case here in this new result is we can take the coupling all the way up to 10 to the 5th. And as I said, this is very, very extreme. Even a coupling of 2 or 4 is actually quite extreme. So, but this was just pushing the envelope to see whether we could even get the training to converge. So we get this very flat distribution. You can see this sharp knee here. But the independent equals one is more like a delta function because the scale has become approximately 0. So let's move on here. So going back to the Bitcoin, if you use a traditional VAE, you get a model here that captures the central parts of that distribution quite well, but it does not capture the tails at all. Even with the multivariate, again, this is a mixture model, so it has some ability to capture some of the tails, but in blue here is the data, and it's not capturing these extreme tails at all. Whereas if we do a model where the coupling is set to 0.6, then we have a model that captures fully these tails. And so that's the innovation here. In 0.6, the variance has already gone to infinity. So it's not super extreme, but it's difficult enough. And then we want to look a little bit more carefully at a more complex data set. We use the Celeb-A data set here, which is these portraits of celebrities. And again, we're going to have the latent space, but we're going to draw from this independent equals variation of it. And I think this is a brand new result. I don't know. I'd be interesting if anyone has been able to do this with another technique. But all of the coupling values converge and give you a model. And in the measure of the coupled free energy on the left here is the training sample, is the training batches. You can see that the coupled free energy goes down, gets better for all of these. However, there's a caveat here in that the metric is changing too. So it's not really a one-to-one comparison. But nevertheless, again, on the right here is showing the epochs of a validation check on this, and we can see how the variation of these is decreasing as we increase the coupling value. But we did want to see more of a head-to-head measurement. So we've also, this was with the MNIST data set where you have handwritten numerals. And here we're training it with the coupled free energy, but we're measuring the performance with the free energy, the coupling equal to 0. And as we had seen in our earlier work, small values of the coupling do create some improvement. So up to 10 to the minus 2 here, and I even think that the 10 to the minus 1 too gives very good performance across the whole, all of the epochs. As you go to higher values with 10 to the 0 here or 10 to the 1, you get performance difficulties. And then as you go more with more epochs, it's actually getting worse. That's not unexpected because we're not optimizing this metric anymore. And in particular, this is supposed to be 10 to the 5 here. The label is wrong. We do see sort of chaotic behavior in this very extreme case. And again, that was actually healthy. I was kind of wanting to see where it would break down. But we still get, but I want to emphasize that, well, we'll get into more metrics in a moment. So just looking at the images itself, this is the original data set, and this is the original VAE in the middle. There's some fuzziness here in this particular model. And then the coupling equal to 1, visually, there's some slight improvements. It's not very dramatic. But as you look at the performance metrics, you know, there is a significant difference. The multi-scale structural similarity shows a 25% improvement over coupling equal to 0, and that stays steady across all the values of the coupling, which again was kind of surprising. It's not really what I was expecting. We see a little bit higher fluctuation when it's 10 to the 5, but we still get reasonable images, or good performing images, I should say. And likewise, the learned perceptual image patch shows a 10% improvement. And again, it's not until you get out to 10 to 5 that we see a degradation with some more variation. This kind of shows our preliminary work on this, but I think what would be of higher interest is now, if we have time, to kind of discuss how this might be applied to active inference models. But just to recap here, so we can now make the training of variational inference algorithms more robust by incorporating a very precise way to train heavy-tailed distributions. And the key innovation here is that we can do that for even extreme cases because of this use of the independent equals modification to the latent distribution. The coupled entropy has these two components. It's a generalized logarithm that forms the metric, and then it's an expectation over these independent equals distributions. So we're quite excited to see how this can be applied in a variety of systems, and appreciate there's a group of papers here, the two recent ones, and then some older papers on this topic. And really appreciate you taking the time to learn about this, and welcome your questions. I'll leave the slides up in case someone wants to refer to them.
Nice.
Actually, what I will do is just...
There's a big line about
Yeah. So are there any questions?
Yes, thank you, Kenric, for your presentation. Yeah, let's open the room for questions, if there is any. I think I've got one, a very quick one on like your model validation. Did you assess like because there's a discrepancy between the inner distribution, latent distribution of the generative model and the one that you use to kind of recover the distribution. So the discrepancy between the one that generates the training samples and the one that recovers the distribution. Did you assess the predictive validity of this distribution? So like, do they, like, does the fact that they, like, for instance, of clamping, like of fitting finite variance distribution to a variance that has infinite variance, to a distribution that has infinite variance, does it hurt like predictive performances?
Yeah. So let me answer it this way. The measurement of when we measure the coupled free energy, that is, and even in that validation chart, that one is using the independent equals distribution draw. However, when we measure the free energy itself with the coupling equal to 0, then we're drawing from the original latent distribution. And likewise, all the other metrics, they're drawing from the original distribution, for a validation process. So the way I see it is the training process would use the independent equals distribution, but your actual implementation would draw from the latent distribution. And it's not completed yet, but I'm planning to do also some discriminative analysis where we want to understand, for instance, in those celeb A images, there's classes that you can define, say like man or woman, or hat or no hat, those kind of classes. We're planning to do some classification tests on the models as well.
Nice, thank you. Other questions from the room?
Actually, too, the earlier paper, just to show that a little bit further too, because there are metrics like that in the first paper. We weren't in that case using the independent equals draw, but we were able to quantify that it improved the robustness of the models. And by that, what we meant is that you could distort the model, you could distort the seed and still get good reconstructions. And it improved both the accuracy and the robustness, which was another thing that came out of that. Because data sets, I think there's sort of two issues. Data sets themselves can have heavy tail type properties in the data. And then there's an additional role for the coupling about being robust against things that weren't in the data.
I see, thank you.
Kenric, I've just noticed that Bitcoin has gone down by 5% today, which means it's lost 45% of its value in the last 6 months.
Right.
Michael Burry says it's going down to 0. Others say not. Does your mathematics help me in any way to decide when I should buy Bitcoin?
This is maybe one of the challenge problems. We envision that our work will be helpful in modeling catastrophic risk, and emerging markets could be one of those cases. So we are looking into that. I think with anything like this, what I would say is the better way to think about it is these models should be able to help you with mitigation strategies.
Yeah.
So preparing, how do you balance your portfolio with the anticipation that these kind of shocks can happen? Not that you can actually predict it one day to the next, but rather that you would have a better way of modeling the possibility of that happening and having some mitigation strategies against it. Yeah.
Thank you.
Any thoughts, Karl, on where this might be of interest in the active inference work?
Yes, I have. I was just making sure that people. Johan usually asks more questions.
Okay.
Yeah, I've got one other question, but I'm wondering whether it is relevant. But did you? I guess I'm still gonna ask it. The fact of having a finite variance distribution, the nice thing about that is that you could build consistent estimator for the like generalized moments of your exponential family. Have you looked at whether such whether like it enables like such like a nice kind of theoretical properties like building
so we're actually in fact Amina is now working on the information geometry of the coupled exponential family. And while I didn't go over it precisely here, there are generalizations of the moments that are based on that independent equals distribution. So for instance, for the coupled exponential distribution, your moment is you're interested in the first moment. The alpha gets replaced by 1, the moment, and you basically take x times the independent equals distribution, and you can show that that equals precisely the scale. And then likewise, x squared times the independent equals moment with m equal to 2 gives you precisely the variance. Well, it's not the variance anymore, but it's a generalization of the variance. So yes, all of the moments then can be defined, but they're generalized moments. And we're working out the information geometry mathematics to kind of prove that those are the best estimators for these kinds of distributions.
Nice. Okay. Thank you.
Yeah.
Yeah. Over to you, Karl.
Yeah, thank you. That was mind blowing. So I should preempt my comments and feedback and qualify. A lot of this is well beyond my comfort zone. It's above my pay grade, so don't expect.
Certainly not. But I understand that it takes time to absorb this point of view.
Yeah, no, and yes, it will. That's the second thing to say, that it's something that clearly needs to be thought about, and particularly in relation to what we were talking about with Anthony at the beginning, sort of modeling fluctuations of a highly nonlinear sort in climate change and food security, but also, as you indicate, sort of modeling to a certain extent exogenous shocks in market prices and the like. I mean, this is clearly a fundamental challenge, and this offers a really interesting potential solution to it. So my feedback is going to be, I repeat, a little bit naive, but may or may not be useful. The first thing to say in answer to your question, would this be of interest in the context of active inference? I think so, absolutely. What struck me was that your reading of variational inference was the optimization of an evidence lower bound, or a variational free energy functional. In my world, variational Bayes would actually commit you not to sampling, but to the calculus of variations to work out the free energy gradient, so that you can either use a generic gradient descent, or you can find the analytic solutions to the minimization or the optimization problem. So yeah. From what I took from your presentation, which I repeat was intriguing, was at the moment you're still in the world of sampling, but the variational aspect comes in virtue of the fact you're using a variational free energy functional to convert an impossible marginalization problem into a tractable optimization problem. And the tractability is nuanced in your world, because there are certain moments like variance which just do not exist. So it is truly intractable in a really deep sense. So what I'm saying, so my comment, could this be useful in an active inference or indeed a climate or sort of fintech context, when looked at through the lens of variational Bayes implementations of active inference? And I don't think we need to answer that question now, but certainly your response to Johan's question about working on the information geometry of this suggests to me that there will be a calculus of variations implementation
Yes.
available that would elude the need to do sampling. But the key point I wanted to make was you can still, I think, very effectively appeal to active inference using sampling, using exactly the tech that you've actually already established. And what I mean by that is that in applications of this kind of variational modeling to climate change or market fluctuations, then the nice thing is, from the point of view of active inference, what you can do is think about evaluating different policies, different intervention strategies. And the way that you do that would be to score them in terms of the path integral of an expected free energy.
Yeah.
Which means that you now have the opportunity to actually use sample paths into the future and just using numerical estimates of the path integral of the free energy, which could now be the free energy based upon the coupling expressions. And you do that numerically, just by, very much like in sort of climate change modeling, just by sort of taking solutions into the future and then just taking the sample distribution of the path integral of the expected free energy as the basis of your comparing the quality of this path versus that path versus that path. So even if you don't at this stage have want to use variational Bayes in the sense of using the calculus of variations to analytically derive the solutions or the gradients, you can still immediately move into the world of path integral control and KL control and risk from an economic sensitive, true risk sensitive control, where you're now actually specifying not just the desired endpoint of your intervention, but just a probability distribution over that, so that you can put sort of economic risk into the.
As you're describing, getting closed form solutions is quite important and part of what we're working on. And as a first step, that's why we match all the coupling values, because the closed form solutions are easier in that case. And so, for instance, the divergence function that we use is a closed form. We don't have to do sampling for that. We are doing sampling on the mean square average, but even that, I could maybe get some nuances and talk to the team about that a little bit more carefully. And then there's two levels. Right now, we just, when we have closed form solutions, we just use the gradients that come out of current machine learning techniques. However, those should be updated given this curved geometry. And that's part of what Amin is working on, is we're working towards, we know we're in this curved geometry space, so what are the new gradients of the system? And then it's harder, there's interest when the distributions and the metric have non-matching coupling values. There's definitely use cases for that, but getting closed form solutions for that is harder. But there may be approximations that could be formed in those cases that would be useful. And then when I sort of was preparing for this, to me, what I see is one of the things that why this could potentially be foundational for the active inference methods is that if you're going to try to move from using these cost functions over a whole neural network, and rather you're going to do updates over individual nodes, then for sure you're moving to a model where there's less data at each node. And that's exactly when these heavy-tailed models become important. So I can kind of imagine a scenario where each node is doing these coupled free energy calculations given limited data, but the whole network still maybe even converges to something more like an exponential model, but it does it in a more robust way.
Yeah, no, absolutely. I mean, and just to put some flesh on that, in terms of the presentation, your focus on the variation autoencoder, I presumed, use backpropagation of errors to
Yeah, we did.
optimize
Yeah,
the weights.
right.
Whereas, of course, if you're going full active inference or full variational Bayes, you would do exactly what you say. You'd make that process much more efficient because you'd be using a local couple free energy function at each node,
Yeah.
and you wouldn't have to worry about backpropagation. You just have to work out the most efficient and graceful possible, hopefully analytic, but not necessarily local gradients, and then you'll get everything for free. The predictive coding people who are trying to sort of
Yeah, we're talking with groups in that area as well. Yeah, that is the direction we'd like to go in.
Yeah, I think that's up. And as you say, once you've got a sort of the opportunity to model these heavy tail distributions or sort of large fluctuations, both locally, I think we'll have a very expressive model there. The other point that occurred to me, it is, I think, easy to see why you would focus on variational autoencoders as a first testing ground to establish supremacy over existing techniques. But I think you should move very, very quickly to state space modeling and dynamic models. That's where the power of application is. I find that sort of people get sort of stuck in a rabbit hole doing MNIST digits and faces and the like for years. They're technique and miss the point. That's not the application. The application is in the dynamics.
I agree. We have about 18 months ago, we did some modeling, starting with recurrent neural networks, but obviously the transformers and other techniques are quite important in the dynamics. So we haven't yet incorporated the coupled free energy into that yet, but I agree completely. And what was exciting actually in reading your work actually was that I also done work in control systems, but I've always sort of traditionally thought of that as like a whole different problem with a whole different set of paradigms. But I loved the way you showed that the utility function is just a prior distribution. And so now I think that makes it easier for us to kind of move into control system kind of problems using the active inference paradigm.
Yeah, no, I think that's absolutely right. And so, ironically, all my colleagues in machine learning think of predictive coding in this very static sense. But of course, predictive coding was a time series model. It was originally introduced to compress sound files, and in the neurosciences, it is the variational inversion of a state space model, usually an extended Campbell-Bucy filter that has nonlinearities sort of built in virtue of using an extended filter as opposed to predictive coding outside machine learning, in its general sense, just is a Bayesian filter. And what you've got, you've now got the maths to do proper extended Kalman-Buzy filtering. And if you can do that, that basically means you can do path integral control whilst accommodating large fluctuations or heavy tail distributions. I think that's an obvious direction of travel. So I suspect that when you talk about your friends or colleagues in predictive coding, be careful. In machine learning, they have a very myopic view of what predictive coding means. They see the important things, which is the locality thing, the eluding backpropagation of errors, having a sort of principled variational functional as an objective function, but they miss the fact that the actual application is in the dynamics. That's where the prize live. I would counsel you do not think of the control theoretic applications as formally different from what you've done already. In many senses, you've just done the easy bit because you've ignored the dynamics. But the power of your maths, I think, will actually be more evinced in a dynamical context. I'd move there as quickly as
that's a good suggestion, right? Right.
Just before I forget, this is not going to be something for you, but if you had sort of masters or PhD students with wanted a particular project, it would be very interesting to look at the formal connections between early models based upon something called sparse coding. People like Bruno Olshausen, who became sort of thought leaders in video compression, about 10 years ago. They themselves were in deep dialogue with people like Tony Bell and Terry Sinofsky and Scott Maykeag. And they basically invented what we currently know as independent component analysis. So what they do, they actually explicitly put a nonlinearity into the process. So instead of working with the right kind of probability distributions that can accommodate the heavy tails, they said, well, okay, I now need to explain these data in terms of some latents. By the central limit theorem, if I've got a mixture of causes which don't have a heavy tail, I've got the wrong causes. I actually want the causes that, by definition, have these fat-tailed or heavy-tailed distributions. So they actually just wrote down a simple state space generative model where they pass through the latents through an unsquashing or a squashing nonlinearity, and then use sort of various tricks to then maximize the marginal likelihood or a variational bound given some data. So it strikes me that would be, it'd be interesting to connect, if you can, the information
that is
geometry.
an interesting suggestion. In fact, Igor is going to be starting a doctoral program later this year in Brazil. So we're starting to think about, what direction that might take. So this is an interesting suggestion. And as you said, like when you get to things like independent component analysis and the Markov blanket, the other thing that's intriguing to me is being able to relax that assumption of independence. Because essentially what I'm doing is that when you have that requirement for independence, what you really have is a requirement to not that all your pairwise correlation values go to 0, right? But with the coupled exponential family, all of those can go to 0, but you still retain this nonlinear dependence. So I can imagine like a Markov blanket where rather than strict independence, I have independence in terms of pairwise correlations, but the systems themselves can still have a nonlinear dependence that can go across the blanket.
Yeah, and I was sensitive to that, and my ears pricked up when you made that distinction. Again, as another MSc or PhD project, it might be interesting to look at that separation in terms of the Helmholtz decomposition. So the dissipative part is the linear part, and the non-dissipative nonlinear part is the solenoidal part. My experience when sort of looking at stochastic chaos that rests upon the nonlinearities, all the heavy lifting, all the interesting stuff is in the solenoidal part. So this is, if you like, thinking about the Jacobian. If you just decompose the Jacobian into a symmetric and an anti-symmetric part, the symmetric part's the linear bit that does the dissipative dynamics with the random fluctuations that are usually well-behaved Gaussian things.
Right.
The interesting things that produce the chaos and the fluctuations of a chaos, an itinerant sort. So this would be sort of, they all live in the solenoidal part. And if you make the solenoidal operator state dependent, which you have to, that's where the nonlinearities come from the point of view of the Helmholtz decomposition. So it'd be really interesting, just from a theoretical point of view, to connect the information geometry of the coupled formulation to, if possible, the Helmholtz decomposition. I think it's it's just the fundamental lemma of variational calculus. It's just decomposing stuff into dissipative and non-dissipative parts, and all the nonlinearities and the interesting bits live in the the nonlinear parts, and that certainly sort of practically keeps hitting you in the face when when you start to explicitly estimate the solenoidal parts as accounting for this itinerant behavior that you get in things like climate change and
that's definitely a good suggestion, because the two models we use the most right now to show this are what's called super statistics, where you have essentially a mixture of exponentials. That's one model. And then another model is multiplicative noise, where you have like some deterministic process. The additive noise will give you the scale, and then it's the multiplicative noise that controls that coupling parameter. But having another model, the Helmholtz, would be great to add to the suite.
Yeah. I mean, the Helmholtz decomposition just gives you a functional form for the nonlinear differential equation. So there might be some deep equivalences there. As you were talking, if you make the what I call the self-information or the surprise, or the sort of the probability density distribution that supplies the gradients to which you apply now your dissipative and non-dissipative operators in the spirit of the Helmholtz decomposition. You can also make that surprise or self-information part state dependent, and it'll look as if it's got state dependent noise, even if the random fluctuations are actually Gaussian and not state dependent, because they're driving dynamics in a changing potential well, effectively. It'd be really nice if there was some sort of formal mathematical isomorphism between these different decompositions. The final thing, which again is another MSc, and perhaps this is even a BSc project, it just your mention of description of these generalizations in terms of the T distribution and its history, which I didn't know about. It did remind me of Jeff Hinton's work on T distributed stochastic neighbor embedding. Have you come across this in cluster?
Oh, yes. In fact, this is a big motivation, actually. So there's an interesting history on what's called the student T neighborhood embedding, stochastic neighborhood embedding. So the algorithm was originally invented using Gaussians, and it was called stochastic neighborhood embedding. The problem is you would get classes that had a lot of overlap to them. And so, yes, you could do this neighborhood embedding, but you wouldn't get very good images because the clusters would be very fuzzy and they would overlap a lot. But when Hinton and Martin, I think it was Martin, added the student T to the model, what it did is it took neighbors that were close to each other and kind of compressed them so that the clusters were tighter. And that's the central part of the peak of the student T. And then neighbors that were further apart were spread away from each other. So the clusters would have separation and more distinct boundaries. So part of my vision for this is that you will be able to do the same thing with your latent distributions. That you're going to learn a model that has sort of tighter clusters of things that are similar and more separation between those clusters. That's definitely one of the things that should come out of this. And in fact, there's some papers in the VAE literature that actually include a feedback loop in order to do something like neighborhood embedding. And that's something else we'd like to add to this so that you, again, improve the quality of the clustering in the latent distribution. Yeah.
Brilliant. Thank you.
Yeah, very nice. It's a coupled exponential. That's my new word for it now. Coupled Gaussian. But yes, it's good.
Well, get used to saying that.
Yeah. But it also, the family is intended to be defined in a way that it preserves the mathematics of this older work. So it's trying to tie it back there, but make it a single family.
Yeah, well, I did notice that when you actually did the expressions, with the usual forms for the sort of the complexity, nice quadratic forms with just that made me think that the information geometry may be easier than it looks, or than one might imagine, given the ambition of this project.
Yeah. So.
I think something that would be interesting to look at, just building on what Karl was saying about the dynamics being one of the next few steps that you might consider. It might be worth to look at the paper chaos as an intermittently forced linear system, where it struck me like the first time I saw the kind of plot that you were showing with this Gaussian like bulk fitting just the most important part of the distribution, and this escape was actually on the Lorentz system, where some part of the so Lorentz system is like this butterfly, and like around like very at the very center of the two wings, the regime is like almost linear and the distribution is almost Gaussian. But when you are at this like extremities of the wing, then you've got this escape. They are quite rare, and they are like quite extreme events that will trigger like a change of wing. And if you look at this, like in this paper, they've got a bit the same plots as you have in the Bitcoin curves. It might be interesting to look at established chaotic dynamical system for one reason, because they are like deterministic systems, but for some of them the actual invariant distribution has been known, and so you could like try to look at the analytic property of your coupled free energy in the case of like very simple like logistic maps or like Rossler systems or Lorentz systems. That might be like accessible first steps towards more complex systems.
Yeah, so in fact, the collaboration with Uygur Türkneli in Turkey is exactly focused on that. He has expertise in simulating deterministic chaos. And we have, Aman and I have collaborated with him on one paper that should be published soon. It's in the last stages of the review, where we invented a new estimator for these distributions. And the examples we used come out of exactly these deterministic chaos kinds of models. And we have some newer work that we're doing now where he's been able to extend these models to many, many decades, showing that the model itself is very accurate. So so that's one piece of it. And then we're also trying to tie it to models that come out of the agent models, but the agents are very simple. They come out of a model of spin glass models that forms a foundation for also modeling socioeconomic systems. And Igor works in this group with Andre Villela on those kinds of applications. And then I think that, but just like you're saying, I think that the next step would be to put on top of these very complex models some sort of active inference agent that can learn the dynamics of these complex systems and then try to come up with strategies of how to behave in such a complex environment. That I think would be the future direction of the work that would be quite interesting.
I have to go to my next meeting, but if you carry on talking, make sure it's recorded.
Yeah, thanks so much, Karl. I really appreciate the opportunity to talk to you about this work.
Great. See you soon. Thank you.
Take care. Johan, as we close out, Igor and Amina here, do you want to take a minute and have them introduce themselves? Are you still there, Joanna? Johan?
Yeah, sorry. Sorry. Yeah, we would assume that MIT has Wi-Fi that is stable, but it is not the case.
Okay.
Okay. thank you for your presentation. I assume Karl is gone now. Thank you so much for your presentation. It was really, really interesting. And yeah, I hope you'll come back soon to tell us more about it. It seems really, yeah, very promising. I'm really curious about the application of that.
Yeah, I'll plan to attend your monthly meetings, and then I am local here in Boston. So if you sort of think of something you want to dig into more, I'm happy to come by and talk with your team about it.
Yeah, that would be really nice. Yeah.
Okay, super.
Thank you, and thank
All
you.
right, take care.